Um, Hi, so I'll present my work titled Robust and Scalable Bayesian Online Change Point Detection. This is joint work with my two supervisors, Jeremiah Noblaus and François Viol. Yeah, the title is kind of straightforward. I'll try to propose like a robust and scalable change point detection model. So first, we will try to present two problem that could think like as a change point, or we'll try to define like what a change point or what kind of type of change point we want to tackle. In the right hand, we have like the FTX scandal, like a cryptocurrency that drops because of the company FTX. So after like bankruptcy, it went down all the Bitcoins and some cryptocurrency and stayed there for time. So we will call this a change point. This is kind of the problem that we want to detect and we want to act. Or in the left hand, we have the Twitter flash crash in 2013, when do like a fake Twitter account, the Dow Jones index drop for like 2 minutes and then go back. When people react to this kind of change, they lost a ton of money. So this kind of thing we don't want to act. So that's like not a change point, and that will be outlier, right? So overall, like change point will be like important enough shift. So we want to model the data differently. We want to compare like in different ways. So in this case, we want to change our behavior. In the other way, no. And we want to use like Bayesian approach to this because we have like different ideas. First, Bayesian give us uncertainty quantification, give us one-step updates, and also predictives. Whereas the idea is to model the one, this is called Bayesian online change point detection. This is the model that we will rely on. And the idea is to measure the time between the present observation and the last change point. And we can see here in the example, here we have like a time series with three different like theta, three different models. So there's a change point, and this will be a change point. And the rank length of this model will be increasing by 1 when we stay in the same segment and drop to 0 when facing a change. So at each time t, we have like t possibilities of where the rank length will be. But that's how this model will work. So now we want to model this or try to follow this RT or rank length of the segment. The model itself, we got like a conditional prior of the rank length, like the previous known on how when will be like a change point or parameters, and the probability model of the data. So the thing we want to infer is the location of the change point, and we will do it by calculating the posterior of the rank length given your data. And this is just, you have this sum or the predictive posterior here, the conditional prior, and some recursion function that make everything faster here. That's one thing that DOCDs works well. And the predictive posterior is, and when the model go in, it's calculated through marginalized over all the posterior of the parametric theta. The thing you can see here at each time t, you want to calculate t times the predictive, because you marginalize over all possible previous rank length. So since the rank length is a discrete variable, you could like discrete this, so it's kind of easy. But since you want to calculate this t times, you want to be able to calculate this like really, really fast. So you want a closed form in these kind of settings. That's why we usually use like a conjugate prior likelihood in this kind of in the DOCD problems. And how this works in practice. Here we have the same two examples, and we can see here, well, the dots here are like the segmentation of the change point that the model found. This is the posterior rank length. So the line marked in green is like the maximum of this posterior of the value. So you can see here the DOCD directly like detect the change point correctly, but in the like left-hand example, find a change point where we didn't want to find a change point, and this is because DOCD is not robust to outliers. It failed when encounter these kind of things. Here we have the other example, and here we can see like the online way that the model works, and this is like the well-logged data, which is basically the measurement of like a real Nahuel, and this like change points are the different layer of the segmentation, like layers of sediments. And as you can see, like the model find like a lot of change point in this kind of period when you don't have outliers, it works fine. But then when you get some outliers, it like go like crazy. So this is most not a BOCD problem, it's more like a Bayesian problem. Bayesian is not robust, and it's basically because it relies on the KL divergence, and the KL is not robust. How it relies, I think we already have discussed this, but the thing is the posterior of the parameters is the prior time and exponential, time minus t of some divergence, and when you consider this divergence as the KL, then you got the standard base posterior, and that's not robust. So the solution we get is use like a robust divergence instead of the KL, and this is called like a generalized base method that already Tokuo discussed. So the question that remains is how to select this discrepancy to get robustness, but at the same time scalability, because we want to be able to use it in an online fashion. So we have like a bunch of possible divergence. We could use KSD, we could use MND or beta divergence. Some of them has like different properties like robustness, but some of them are not scalable, or they are both, but they don't give us like these one-step updates. So we went from the diffusion score matching, which is basically the score matching presented before, but weighted with this M function M. Score matching is just like the expected square distance between this score function, which is the gradient log of the density. The M function, why we choose the diffusion score matching on DSM? Because this M function will be the one that will guarantee the robustness of this method. The problem is in this setting, we don't have access to the density of the true generative process. The idea of the DSM that we want to calculate is this is the model, and this is the true generative model. We don't get access to this, but after some tricks, we can rewrite this like this. When we get rid of the score of the true generative model, so have like this form as a C that doesn't depend on theta, so that's good. And after that, if we want to calculate the divergence between the empirical measure and the model, we just have to deal with this term over here. So that's the future score matching. How we plug into the DSM base, I mean, in this, sorry, I will present now the proposed DSM base, which is basically plugging the diffusion score matching that we presented before in the expectation over in the exponential over there. Thank you. So is it good or bad how it will work? First, we will focus on scalability because we want to be able to use it in the BOCD. And as we can see here, it kind of follows the same idea that Tokuo already presented. It has this property of conjugacy between exponential families and square exponential forms. So if your model is from a square exponential and your prior is square exponential, I mean, your model is exponential family and your prior is square exponential, then your posterior will be square exponential again. This means it doesn't have to be Gaussian, it can be like truncate Gaussian or so on. So this is work with parameters that are just defined over the real like positive values. Here mu and sigma has this formula here, which is which are cheap to compute. Nu and lambda are function of the R and more like the parameter of the exponential family and the M function. But the good thing, they have this form. It has like the form that an average of nu of the data. So you could split it like, and you get, and actually you get these one step updates. So you have like the sigma t is a function of sigma t minus 1 plus this function lambda t, and the same with mu t, which is kind of nice because now we have scalability. We know that we can use it for exponential families, and also we get these one-step updates. Now, discussion about robustness of this method. Is it robust and we will work in the setting that we want? Here we have an example that I already have presented a lot of people here, a contamination model. We have the DSM posterior and the standard posterior predictive, and we see that the standard is influenced by the contamination, but the DSM kind of concentrate in the correct data, which is kind of encouraging that the DSM works well. But we want to prove this like in a theoretical way. So we go to the setting of standard robust statistics that I think also Takuo is, we will rely on the work of Takuo. So basically, when you have an estimator and a contaminator distribution, you define the influence function as the influence of the contamination over the estimator, right? As the derivative with respect of epsilon. And we call an estimator robust if the influence function is bounded. An example here is the mean function, the mean estimator, and we see like the estimate is not robust, right? You have the mean here, and if you add some contamination, will move. And using this framework, the expectation, the influence function of the mean is just y, and then the supremum will be infinity. So that's why the mean is not robust. You can extend this idea to posterior distribution, but now you define, you have to be like bounded in the two parameter in theta and y. You define as the same idea. You have like the influence of the posterior given your contamination, and if you posterior is bounded over theta and y, then you call a posterior robust. We can simplify this a little more, since if you have this the posterior of this form, and the form that we have, like is exponential of minus t for times divergence, you can simplify this to the robustness of the divergence itself. So you define like the divergence sensitivity at theta to the perturbation y as the same as before. It's just the derivative of the divergence given epsilon, and that is how the divergence move if you move the contamination of the contamination. So you can get these two sufficient condition that to show that up posterior is robust or not. So if the divergence fulfill these two conditions, then you know that your posterior will be robust to outliers and misspecification. So how works in our setting? Well, if we are again in the, we have a model from exponential family, a posterior square exponential, and now you select the M function as this. We propose this, then you can prove that the posterior is robust. So if you are in this setting, you are exponential family, and you select the function, the wave function M as we propose, then we can prove that this posterior is robust outlier and will work well in the setting that we want. Everything is clear by part? Sorry. So how you plug in now back to the DSM to the BOCD? How you plug in this into the BOCD framework? You basically replace the standard posterior in the predictive with the DSM posterior. You know that this will be, if your model is from exponential family, this will be a square exponential. So this is just the base posterior that has two main properties: is robust outliers via smart choice of M, and it has closed form updates from exponential families. How does it work in practice? Back again to the two main examples. You can see like here, this is the blue line is the robust, the standard is the green one. You can see that here find the same change point, which is kind of cool, because sometimes we could think that may not find the change point that we want, but at the other example, we didn't find any change point that is really good. We didn't want any change point there. Again, the same example with the well-log data, and again we can see like an improvement, like a big improvement from the standard BOCD. here, when the standard got crazy, we didn't find any change point as well, like these two like outliers. In terms of computation advantage, here we have an example where the standard VOCD wouldn't work, but in our case, it does. We model the UK government bonds as a gamma distribution, since all this is just defined as a positive values. And the DSM gives closed form, but the standard procedure doesn't. You know that for the gamma distribution, you got a conjugate prior, but you don't know the condition, the normalization constant, so you cannot get this in closed form, in actual closed form. And in our case, we will get closed form. So now we can show that there is some example that we get closed form where even when the standard doesn't. So that's also like a good improvement to a standard VOCD case. Also, it's kind of nice that the segmentation that the model finds match with some event in the UK, like different like COVID waves and when Liz Truss won as a prime minister, or like different political events. So in summary, we want robustness. All my are not perfect, and we want to deal with these outliers. Otherwise, we will get a unnecessary change point that will cause some problems in our setting. It is natural to be Bayesian for change point detection because give us one-step updates, uncertainty quantification, and predictive. But the standard-based inference is not robust; it's easily full to outliers. So we can rectify this by using the DSM posterior, which is probably robust and computational feasible. That's it. Thank you. Was it too short? Yeah.
I was just wondering whether you can motivate your initial model a bit better in terms of the run length, because it seems like more natural to just monitor the values of the parameters as time goes on, compare them to what you think the current model is, and then mark the change point when that's a deviation too large.
Oh, okay. Yeah, the thing is, the idea of the VOCI improve one of the key point of this is like you can apply this to whatever model you have, so you are not restricted to any model. So that's kind of when you are trying to use like a frequentist approach, you have to like to stick with one model, say like a Gaussian or something like that. So
but you still need a model of their run lengths, right?
Yeah, but you can also check. This is just like you can extend the VOCD to have like different models in each run length. So you have like a family of models, and you can pick like with probability whatever whichever model you have.
And what about like the setting that you showed in your first example, where there was no obvious run length, right? It was just a single event, and we can kind of intuitively find the change point.
Yeah.
Run length model.
Yeah, that's a good question. Yeah, I have no response for that. Sorry. Yeah.
Any more questions?
I was just wondering, so you mentioned that kind of in the example you don't see any loss of kind of sensitivity necessarily compared to is that a case across all the events?
Yeah. There were some cases that the model didn't find a change point when the standard case did, but it was really rare. Usually was as well as the standard case. Also, I can show like have like an extra. Sorry, this here. Here we have like a table, which is this is like the positive predicted value, and this is like the true positive value. This is like how many false change point you find, and this is measure like the true values. You can see like you get like almost the same result as the standard base, but you have like a big improvement in the false rate. Mm-hmm. Yeah.
Yes.
Give some intuition as to what the function is actually doing. Like if I wanted to construct one.
Yeah, that's cool. The M function try to the M function is give like weights to try to put weights in the places that you want to. In this case, we want robustness, so we don't want too much weight in the tails. So you kind of try to forget this. So that's why we choose like this kind of M that control the likelihood the derivative of the likelihood to not like explode at the tails. That's
Cool. That's it. Thank you.